Hi everyone, in today's video we are going to talk about solving exponential and logarithmic equations. In order to solve, we're going to be rewriting exponential expressions to have the same base, and we're going to be using the exponential and logarithmic equation. We're solving exponential and logarithmic equations by using a few properties. The properties of exponents, the properties of exponential equality, the properties of logarithms, and the properties of logarithmic equality. So let's get started. The property of equality for exponents say that if the base is the same, then the exponents must also be the same. So if I have 3 raised to the x is equal to 3 raised to the 5th power, that means because the bases are both 3, that x must equal 5 as well. So let's look at how this will help us. If we're in a situation where it's convenient to rewrite the bases, then we can rewrite both of those bases to match, and then the two exponents can be set equal to one another. So let's look at this first example. I have bases of 9 and 27. 9 is 3 squared, and 27 is 3 to the 3rd power. So I'm going to rewrite each of those bases. I'm going to write 3 squared raised to that 2x power is equal to 3 to the 3rd raised to that x minus 1 power. Now, according to the exponent rules, when you have a power raised to a power, you multiply. So this is 3 raised to the 2 times 2x, that's 4x. And then I'm going to multiply on this side, which means I'm going to distribute that 3. So my base is 3, and then 3 times x is 3x, and 3 times negative 1 is negative 3. Now I have two bases that are the same, which means that the exponents must also equal one another. And then from here, it's just a very basic algebra 1 problem. So I'm going to subtract, and I get that x is equal to negative 3. Now, after you solve for that variable, you should always check your solution. The way that we're going to do that is by taking this x is equal to negative 3 and plugging it back in to both sides and simplifying down with a calculator when helpful. For our purposes today, to keep this video short, I'm not going to go through that step, but you absolutely should check for extraneous solutions by plugging the answer back in. Remember, you can also check graphically by graphing the left-hand side, graphing the right-hand side, and if the intersection has an ordered pair that the x value is negative 3, then that also works. This one, I'm going to just say it does work no matter how you check it, and let's go ahead and move forward. So let's try a couple of practices. In this first practice, I have a base of 3, but my other base is 1/9. Now I know that if I move the 9 to the other side of the fraction bar, the exponent becomes a negative 1. And then I know that 9 is 3 squared, so that means 3 to the negative 2 is a way that I could rewrite 1/9. And then I can use my exponent rules to do this multiplication. That's distribution that's happening. So I'm going to distribute and get negative 2x minus 6. And then my exponents are going to be set equal. X is equal to negative 2x minus 6. That means then that I need to add 2 to both sides and then divide by 3. And I get negative 2. Again, you should check these for extraneous solutions. I'm going to try to save some time and skip forward. This next one has a base of 81 and 1/3. 81 is 3 to the 4th power, and 1/3 is 3 to the negative 1 power. So again, I'm going to distribute my powers because that's power raised to a power. So that's 12 minus 4x is equal to 3 to the negative 5x plus 6. And then I set my exponents equal to one another because the bases are the same. From there, I am combining like terms, so I'm going to, let's see, I'm going to add 5 because that gives me x on this side. I'm going to subtract 12. That gives me negative 6 for my final answer. Okay, so let's go on to a second situation. In the second situation, we're going to use the property of logarithms, which is very similar to what we just did with exponentials. In this situation, if you have logarithms that have the same base, so in this case log base b, then the input values, the x and the y, are also going to be equivalent to one another. So if I have log base 2 of x is equal to log base 2 of 7, that means that the inputs x and 7 must equal one another as well. All right, so, and these is going to be more important than exponentials, but we still, again, always check for extraneous solutions because you will have them in exponential and logarithmic equations. Okay, so for this problem, or this type of problem, we cannot rewrite the bases to match, right? We have a 4 to the x and an 11 to the first power. 4 and 11 are not going to be some small base that matches. So instead, we're going to use logarithms to undo the exponential part. So in this one, I'm going to take the log of both sides. When I take the log of both sides, then I can use the rules that we did when evaluating logarithms. That brings this power of x out to the front to be x times the log of 4. And then I can divide by the log of 4 on both sides. Because when I do that, those log of 4s cross out or divide out and leave me with x is equal to the log of 11 divided by the log of 4. Now, this is my exact answer. If I wanted an approximate answer, then I could plug that into my calculator and I'd get approximately 1.73 as that approximate answer. For either of these, you can plug them in, again, to check your work. I would do 4 to the, if I wanted the approximate, 1.73, and when I plug that into the calculator, it should give me about 11. It might be a decimal off, hopefully should be very, very close though. If I used log of 11 divided by log of 4 in that exponent, then it would have given me exactly 11. Okay, so generally we're going to use just log base 10s because it's the easiest thing to use. It's the most simple thing to use when we have two bases that we cannot rewrite as bases that are the same. It's not convenient. Now, the exception to using log base 10 is if we have an e in our problem. So if you look at practice problem number 3, I have e to the negative x is equal to 5. Because I have that natural log, or that e, I'm going to use a natural logarithm because natural logarithms and the Euler number e are inverses of one another, so they undo one another. So in this one, because there's an e, I'm going to take the natural log of each side. I'm still going to use the exponent rules to bring the negative x out front. That's negative x times the natural log of e. But then instead of dividing by natural log of e, natural log of e is just 1 because they undo one another. So that's negative x times 1 is equal to the natural log of 5. Or in other words, negative x is equal to the natural log of 5. Then all I have to do to get the x by itself is multiply each side by negative 1. So the negative natural log of 5 is my final answer. I can plug that in and see what the calculator gives me. It should give me 5 when I plug that back in to check my work to make sure there aren't extraneous solutions. The second type of problem that we're going to solve is a logarithmic problem. So in the past two, we had exponent or exponential. So I had a base with raised to an exponent with an x in it. This time I'm going to have logarithms. So if I have the same type of logarithm on both sides, so in this example, I have log base 5 on the left and also on the right. Remember that equality property we just talked about said that the interior of these two, the inputs 4x minus 7, should equal x plus 5 if I'm solving. And then this is just an algebra 1 problem. Now this only works because they're both log base 5. If they weren't, we would not be able to use this sort of situation because they aren't the same type of logarithm. In this case though, they are, so I can subtract x, I can add 7, and then I can divide to get x is equal to 4. The last type of situation is when I only have a logarithm on one side. Now to do these, we are going to isolate and then use exponents to get rid of the log. So I need to isolate the part that's the logarithm first. So that means that this minus 3 on the outside needs to move to the right hand side of the equation. So I'm going to add 3 to both sides. And now I'm ready to use exponentiation. What that means, remember from before, is that we're going to take this log base 4 and turn it into an exponential. Remember, the way that we do that is we start with the base, we raise it to the power, and then it's equal to the input. So 4 to the third power is equal to 5x minus 1 is the exponential form. Now from here, it's pretty easy to solve, right? We have 4 to the third is 64. We're going to add 1 to both sides, and then we're going to divide by 5, and that gives us our answer. When we plug it back into the equation, we plug it into the calculator, we'll get 0. That works. Okay, so let's do 2 last quick examples. Number 4 is log base 4 on both sides, so that means the 2x plus 8 is equal to the 6x minus 12. I'm going to subtract 2x, which gives me 4x. I'm going to add 12, which gives me 20, and then I'm going to divide both sides by 4, so x is equal to 5. On the number 5, I have log base 7 on one side and a 2 on the other. I don't have log base 7, so I can't just set the interiors equal to one another. Now in this one, I don't have anything to isolate because the only thing on the left-hand side is this logarithm. So I'm going to exponentiate, meaning I'm going to take my base, raise it to the power of the other side, and that's equal to my interior. So 7 squared is equal to 3x minus 2. 7 squared is 49. I'm going to add 2, that gives me 51 is equal to 3x. And then when I divide by 3, that gives me 17. Yeah, 17. And that is my final answer. I can plug it in to check and make sure it works. Okay, so let's talk about what we just did. We rewrote exponential expressions that have to have the same base if they weren't convenient and didn't match. We also then solved exponentials and logs by using those properties, the properties of exponents, the properties of logarithms, and the properties of equality. Go ahead and try the Now You Try problems.